future reference. And then the plan is we'll go through the basic circuit first and show some simulation techniques that you can use. Some of you might already seen that in other courses too. But I do have a circuit called Autic PSS PAC demo. It's found in your library manager. The font is pretty low here, so I can't show you that. I mean, it's probably hard to see the font, but Autic PSS PAC demo. And then we have a couple of different analyses. Let's move my head away. So it's called PAC and PSS. I'm going to move some stuff here so I can. Let's move my head away from the picture a bit. So let's move it here instead. Okay. All right. So there is a PSS, which is a periodic steady state. So you who are taking the RF course has probably bumped into this analysis type. So what that analysis does is that it assumes there is a steady state, that you have like a behavior which is cyclic and periodic, repetitive, which a sinusoid is, for example, or a square wave, or anything that repeats itself with a certain bandwidth. So a sinusoid typically has, you know, extremely low bandwidth, like 0. Just exists in one single frequency, whereas a square wave has several tones associated with it. At f0, 3 times f0, 5 times f0, etc. So for simulating a square wave, we would, to get an accurate result, we will typically need a very wide bandwidth of our simulator to capture. Otherwise, we will get artifacts of our simulation. But for sinusoids, it's pretty useful. That's the message, because we have a narrow frequency, so it's easy for the simulator to find this steady state behavior then. Okay, so periodic steady state, and then there is a that's going to give you the transient result simply, the steady state settled behavior. So it's not going to give you all the startup behavior. For example, when you turn on the system, for example, in our SWITCAP case, you're going to have a scenario where you start switching the switches back and forth in order to charge all the capacitors. And then after a while, you will reach a sort of steady state where you move or shuffle charge around the DC value or a sort of offset point. So working yourself up from 0 volts up to VDD half, for example. And then the signal is sort of fluctuating around VDD half. But the PSS will then just give you the fluctuation, not the settling behavior. So that's important to know. In addition, there is something called PAC, which is a periodic AC analysis, which is very powerful. It will also take the steady state behavior from the PSS analysis, and then it will do a frequency analysis around that steady state point. So why would we like to use this for our simulations? Well, that's exactly what we're doing in our SWITCAP circuit. We have a quite aggressive sampling frequency, sort of chopping up the signal or making, you know, odd things with the signal. So from a transient point of view, there's a lot of things happening, but from a steady state point of view, it will, you know, repeat itself. Even though I sample with a high frequency on top of my signal, that repetition of sampling frequencies on top of my signal is repeating itself. So that means I can actually consider my SWITCAP circuit to be a mixer. I have my base frequency, F signal, and then I have my mixer frequency being F sample. So I can use the same tools that I sort of use for my high frequency RF analysis. So PSS and PAC are really useful. And then I've also added a transient here to illustrate these effects. So In this particular circuit, we use this low pass filter that we talked about on lecture 3. So I'm going to just give this slightly better values, 10 picofarads and 20 picofarads, something like this. And I'm going to turn off PSS and PAC at the moment, and then just run the transient. So if you remember this part in the middle, I have my switch, and then I have my capacitor. So this is my resistor, or switched resistor. And then I have a load capacitor. Back then we did sort of 2 approaches to find the transfer function. First, we assumed this was a resistor, and then we had a capacitor, and then we calculated the pole as the R equivalent times the C load, and found out that it was slightly incorrect, that we had to do a more accurate analysis. Due to charge sharing, half of the phase, or sorry, one of the phases, C switch will be in parallel with C out. So C out will steal charge from C switch during one of the phases. So we had to do a little bit more of an accurate analysis. In fact, if you remember, we had, using the switch capacitor as an RC link in this fashion, we had to cater for the fact that C2 steals charge from C1 during this phase. So they are in parallel there. So we couldn't just multiply and be happy. Instead, we did a charge analysis, and we ended up with a discrete time transfer function like this. V2 divided by V1 equals to something. And then in order to translate this to the continuous time world, we could set Z equal to e to the st on the unit circle and do our Taylor expansion, 1 plus st. We could rewrite here, blah, 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 and then write that as a Bode's normal form, 1 over 1 plus s, and then effectively we get the pole here being C1 times the sample frequency divided by the sum of capacitors. Anyway, so let's look at the transient behavior. My simulation window is somewhere. Oh, I'm in the wrong window. Here we are. Okay. The button 2, by the way, in the Daisy flow is quite handy to get this direct plot form window. So press button 2 in your schematic window. Transient, voltage, and then add to outputs. For example, select V out and V in. Okay. Yeah, so in this particular case, we're running a pretty low frequency, so we're probably passing through this low pass filter without attenuating much, hardly anything at all. And there is hardly any phase shift either. You see the red output curve tracks the input yellow curve pretty well, so we're at a low frequency. We could try and increase the sample frequency. Here we see the sample frequency is 200 megahertz and the input signal is 2 megahertz. So let's lift it up to 20 megahertz. This we did also in the lectures. Okay, so obviously we run for a shorter period of time. That's another tip, by the way, once you run your simulations here. A tip is to set the stop value of your simulations to be a function of the signal frequency or function of the sample frequency. So here I defined a parameter T stop, which is, yeah, might be difficult in the camera here, but it's a certain number of periods over clock signal frequency. So that means I can always, let's see if we can do some zooming like this. I can always specify a constant number of periods in my simulator. That's a pretty handy way of doing it. So try to parameterize everything in your simulations. That saves a lot of time. Anyway, so I still simulate the same number of periods here in my simulation graph. 8 of them, it seems, and then I have 8 periods also at the lower frequency. So here we can see the blue one is the input signal, the green one is the sampled, and now we see there is a loss in amplitude, and there is also phase shift happening here. So I'm approaching the pole of my system. Okay, so one thing one could do now is to simply run the sampling and the transient analysis and maybe loop the signal frequency and measure where do we lose X dBs or something, or a certain amplitude level. And then you can find the bandwidth of your system in that way. So it's obviously a bit tedious. Transient simulations are quite time consuming, and they're also power hungry, memory hungry, etc. Sorry, disk space hungry. So that's why we can use the PSS and PAC analysis. The PSS is pretty simple to specify. You more or less pick up the information from the variables automatically. There is a certain field here called number of harmonics. Let's see if we can do that trick again here. So number of harmonics down here, 32. So that implies the width of your band that you want to simulate. So this essentially says I want to look at 32 harmonics of 23 megahertz. So I'm going to tell the simulator to be really accurate if it would be a square wave signal here. For a sinusoid, it's pretty well defined for a low number of harmonics if it's not distorted or something like that. But 32 is an aggressive number, so we can probably reduce that to 6 or something, for example. I'll let you dig into the details by yourselves. Let's see if we can make this window a little bit more useful. Okay, so let's see what the simulator reports now. So just press play, and let's get rid of those guys and just look at the okay, yeah, sorry, I forgot demo version. I have to update here, so okay. All right, so now we can also perhaps plot the transient curves also. There we are. Okay, so this is my transient analysis that we did. This is the result from the PSS, periodic steady state. So it has found the sampling behavior that it expects on the signal. So we can, for example, compare that with our transient simulation, and we see that they are more or less on top of each other. There seems to be a certain time delay between them, but that's quite natural because the PSS has no idea really of the starting point of this steady state behavior. So it's just going to select a certain time point and start from there, whereas my transient simulation really knows where 0 is 0, sort of. Okay, but perhaps more importantly then, especially for your filter designs, is that we also get the frequency response from 0 to half the clock frequency. So up to 100 megahertz. And here we do actually have the low pass filter that we see from the analysis we did on the lecture. So 1/1 plus something. So we see for low frequencies here, we have a gain of 0 dB, so that's 1. And then, yeah, at some point it starts to lose power, and then we're down at 3 decibels by 35 megahertz roughly. And actually we can also see that here on the tool if my head wasn't in the way here. So here we see the calculation from the test bench that it's 35 megahertz. All right, so then we can use the analysis to do more clever simulations. So for example, parametric analysis, I could now sample or simulate the sample frequency from 100 megahertz to say 500 megahertz in 5 steps, and then run this. So let's see. For the demo, it's pretty fast after all. All right. And yeah, then I get a lot of curves. So we can see in the transient analysis, we do have, let's see if we can make, you have all these different varieties of the transient. So even for the human eye, it's a little bit difficult, or especially for the human eye, it's difficult to analyze them. So let's get rid of that one for now. And let's look at the nice feature with the AC analysis, periodic AC. So now it simulates and finds the bandwidth for all these different sample frequencies. And if we go back to the equation again, you remember the pole here is given by C1 divided by T, or C1 times F divided by C1 plus C2, that's my pole. So it's going to scale linearly with my sample frequency. So here we have the AC characteristics, but we have also derived the points, the bandwidth points here on this side. So it reports, you can't read probably, but 17 megahertz, 34 megahertz, 52, 69, and 87. So yeah, you can see it's pretty well linearly scaled here. So the equation seems to hold to a good degree. So yeah, so take a look at that test bench, the ATIC PSS PAC demo, to help you understand what kind of simulations you can do. And then further on, I mean, not only the sample frequency, you can hear quite easily also switch R on, for example. If I could just type on the right keyboard. There we are. We can simulate switch R on maybe from 10 ohms up to 10 kilo ohms. So what I'm doing here now is to mimic that I do have some parasitic resistance in my switches. And the higher resistance I have, the more settling behavior I expect. And yeah, so let's zoom in on something. Can we make, let's so I'll just be removing some of the, so you get a better zoom in the picture. All right, so there maybe. Yeah, so first of all, the transient shows here then for different, this is for the blue one, almost straight line is for really high resistance system, and obviously doesn't work. For 10 ohms, okay, seems to be pretty good. We can zoom in on the settling here, looks fine, reaches the N value, etc. But we can also then go to the PSS analysis, which gives us for one period. So we can take a look at what it looks like for different phases in my sweet cap circuit. Yeah, you obviously see the sort of typical RC behavior of a our single pole system. So e to the minus tau divided by RC or something like that. So 10 ohms is fine. Some other ohms, which I can't read here. Let's see. 60 ohms is the yellow one. Green one is 320 ohms, etc. And there you see it starts struggling. And also the yellow one is struggling because it doesn't reach the N value. So the settling does influence the result, even though it's a low number, only 60 ohms, which is not much. Sort of looks fine. It looks like it settles, but actually if you look at the whole scale, you lose amplitude here and accuracy if it would be a data converter. And the green one is, yeah, sort of beyond help then. And you also actually can see here quite clearly in the picture that we do have two different phases in our design. So we have one charge phase and one hold phase. And that also makes sense. If we look at the circuitry here, we will have one phase when we charge the capacitor, and there's one phase where it's held. Since the switch is pointing in the other direction. So it sort of makes sense that half of the clock cycle will be independent of the settling behavior. So this chunk here where it's just a straight line, there's no switch involved in the equation sort of. All right, so it's a very handy way. So this very simple test bench is my suggestion that you sort of look into. ATIC lab, ATIC PSS PAC demo _T, and run through some tests there. There are also mentioned somewhere in the reference material. And one can play around with other parameters too here. All right, so let's kill this one. Do I want to save? Yeah, let's save. So let's call that seminar demo. Okay, then you're supposed to focus on the accumulator. So I'm not going to go through all details here, but just to illustrate the conceptual differences. So here I have one ideal accumulator, the parasitic sensitive one with an ideal op amp. So this might require some explanation. It might not be doing exactly what you want it to do. So you might have to maybe do some modifications to this. What this does is it takes the parameters DC gain, pole location, and the capacitance. So you can sort of specify the points, the 2 points in a Bode plot that determines this single pole system. And then you can sweep them. But maybe you want to sweep some other parameters to understand your circuitry. But at least take a look at what's happening inside here so you understand what's going on. And that's parameters then, capacitive load, DC gain, and pole frequency that you pass on to the circuits. So a lot of parameters that are also picked up by the simulator. And then you have the same, but with your op amp. So in this case, there is this default op amp settings included. And let's just look at the output. So the template you have is with transient analysis. So we can just illustrate what's happening. Yeah, takes a little bit longer time here. It shouldn't be this slow normally, but I think I didn't select the fast simulator, so let's await. Okay, 100%. Okay, button 2 for the menu, transient, and look at the ideal output and the V out of your op amp, or whose op amp it is. Something like this. We can zoom in on different sections, and yeah, you see that the ideal one behaves pretty fine. There is a settling behavior. We can see a weak settling behavior going on here. So there's something related to this pole that I told you about and the beta. We also see a sort of similar type of behavior that it seems to hold its value pretty well during the other phase. And that's the same thing. We disconnect the switch from the op amp, so it doesn't have that much to do during that phase. So the red one is the ideal one. The blue one, sorry, yellow one is the non-ideal one. So first of all, you have a slight settling behavior going on in the beginning. There is something, you have to charge internal nodes and voltages to turn the machinery on. So you have to remember that when you run your simulations to find, for example, some amplitude levels or something. Typically, it's better to look at the end of the graph instead. If you look for example, min versus max to find an amplitude. We can also take a look at the phases, and here you see they behave quite differently from what you expect on the ideal op amp. So there seems to be some glitching behavior happening here. They don't look like square waves. They don't hold the amplitude like you would expect. It doesn't provide you the amplitude you would like. It seems to be half the amplitude, etc. So why is this? What are the factors that limit this? So that you have to investigate. We could, for the fun of it, just take a look at this common mode voltage. So now I plot the common mode voltage of the ideal op amp. So we see it's well defined around the 600 millivolts VDD half level. It has some switches. Let's plot the other one. Oops. Now I plot the common mode voltage here. Okay, and then you see the issue that we discussed today in the init session. So ideally, if this would be an op amp with an infinite gain, there would be just a straight line at 600 millivolts. In our case, the ideal one also has some flaws. It's not perfectly limit the gain. I think the gain is something like 1,000 or something. In fact, we could actually look at that. The gain is, well, yeah, exactly 1,000. But the op amp looks like, yeah, quite bad op amp, and the swing is, like I said, yeah, it's plus minus even more, roughly 100 millivolts up and down. So in this particular case, the gain is quite bad. And obviously this affects the result somehow. So it explains some of this odd behavior of the op amp output then. All right, so yeah, and then we have plenty of ways to, with parameters, change the on resistance, pole locations, load capacitances, etc., etc. I haven't added Pss analysis here, but it's pretty straightforward. Pss, and then get some frequencies, etc., etc. But I'm not going to, I think, waste your time with that right now. It's pretty self-explanatory once you open the tool. So I think the key issue with this lab, or the key message with this lab, is to understand these particular things. If we compare, the ideal with the non-ideal one, so take sort of a walk through the different nodes and voltages and compare them with each other, and see how does your design differ from the ideal one, and perhaps understand why. So for example, we could gain be the issue? We know our circuit has a really poor gain, so let's try to change the ideal op amp to 40 and run a simulation. And then, sorry, it was pretty lengthy simulation, but I think you understand the message. So you can now take the model, and then you would do, revert back to a low gain, maybe the pole you have an idea of, 500 megahertz bandwidth, etc., etc. So you just plug them into your model and compare them. Do they match? Then you have the answer to the questions. If they don't match, then you have to search further for something else. So let's see. Okay, so the V ideal one. Let's see if we can get hold of this somehow in a clever way. Yeah, hard for you to see because it picked two green colors. So we had the first ideal one, pretty much a straight line, and then we have another green one, dark green for low gain. Yeah, maybe this picture is even better. You actually see that the dark green one has higher swing here compared to the bright green one, which is straight. Yeah, this was a good picture. Yeah, so here we have a pretty good explanation to parts of it. So we see the green one, it fluctuates by a factor 20 millivolts or 10 millivolts up, and the signal swing was 100 millivolts or 200 millivolts maybe. So there is something related to the gain there. So that probably explains some of your op-amp limitations, etc., etc. So you can also set the pole frequency to a much lower value, etc., etc. Okay. Any comments or questions on this? Some of you are probably quite used to cadence. I've been working with cadence since 1994, and I'm pretty used to it. So if you need any other tips or want some tips on how you can do stuff here, then please let me know. There is obviously the entire skill script language support and Python support for cadence, which you can invoke and run more extensive tests. You can run the ADEXL one, which with different sheets, etc., for testing your devices. I haven't really created them for this lab series. It's up to you to test around. Okay, so now we had the pole frequency was much lower, and now we have an ideal voltage, the green one. And now we see that the green one with poor gain and poor bandwidth. Sorry, I'll remove my head here. Okay, sorry. Yeah, so last words from me. So I reduced both the gain and the bandwidth of my system. And now we see that this, funnily enough, another green one for the ideal one, more or less looks actually like the op-amp one. They are almost actually identical to some extent here. So it seems like we mimic our transistor implementation quite well with that assumption. Still, it looks a little bit better actually on the output than does the op-amp, but yeah. Okay, so a pretty good model to understand your circuit and also specify your circuit. What's more harmful for you? Is that the gain, or is it the bandwidth, or is it the unity gain frequency or phase margin, etc.? So play around a bit and try to understand that. Okay, so I'll talk half an hour, so I'm going to stop there. Unless there are some questions on the chat or so, I'm going to